Welcome to lesson 2.7 on assessing a regression model. After this lesson, you should be able to use a residual plot to determine whether a regression model is appropriate, interpret the standard deviation of the residuals, and interpret R-squared. So essentially today's lesson is about deciding whether the linear regression model that we fit to the data is a good fit, and how good of a fit is it. So the first thing we want to talk about today is called a residual plot. It's essentially taking our scatter plot and making a different scatter plot using that same data. So we're going to use residuals to assess whether a regression model is appropriate by making a residual plot. A residual plot is a scatter plot that plots the residuals on the vertical axis and the explanatory variable on the horizontal axis. So remember, the residuals are just how far those actual dots are from the predicted regression line. So here we've got an example. We've got a scatter plot showing the relationship between Super Bowl number and the cost of a 30-second commercial for the years 1967 to 2013. So on the left-hand side, you've got figure A there. That's our regular scatter plot. We've got which Super Bowl number we are looking at, and we've got the cost for a 30-second commercial. And then we've graphed our regression line. Now, right away, I'm going to look at that regression line and think, maybe a linear model is not the right model. That scatter plot looks more like a curve than it does a line. But I can drill down on that and look to the right at this next graph, which is called a residual plot. And I want you to look at the change to the axes. The x-axis stays the same. Our explanatory variable is still Super Bowl number. But instead, what we've graphed on the y-axis are the residuals, how far those dots are from the line. We will use Google Sheets to create these residual plots. We're going to attach an additional Google Classroom video so that you don't have to do this on your own. You're definitely not going to be doing this by hand. So what we see by that second scatter plot there is that the least squares regression line clearly doesn't fit this association very well. In the early years, the cost of an ad is always greater than the line predicts, resulting in positive residuals. So that's why the dots are above that red line. But from 11 to 33, the actual cost is always less than the line predicts, resulting in negative residuals. After Super Bowl 33, the actual cost is almost always greater than the line predicts, again resulting in positive residuals. This positive, negative, positive pattern in the residual plot indicates that the linear form of our model doesn't match the form of the association. A curved model might be better in this case. So let's look at one that does make sense. Think back to our data about the Ford F-150 that we've looked at before, along with the corresponding residual plot. Looking at the scatter plot, the line seems to be a good fit for the association. You can see that the line is appropriate by the lack of a leftover pattern in the residual plot. So if we look back, essentially, that curved residual plot in figure B, that's bad. A scattered amount of residuals around that red line is good. The residuals look randomly scattered around that residual line. Interpreting a residual plot works like this. If there's no leftover pattern in the residual plot, the regression model is appropriate. If there is a leftover pattern in the residual plot, the regression model is not appropriate. So essentially, if you were a real statistician, at this point, you would not move forward with your linear model. You would say, no, this looks like it would be better fit with a curve. And so I would not move forward with calculating my correlation coefficient or any of that, which is only appropriate for a linear model. Why do we look for patterns in these residual plots? Well, remember, the word residual comes from a Latin word meaning left over. When we calculate a residual, what we are calculating is what is left over after subtracting the predicted value from the actual value. When we look at the form of a residual plot, we are looking at the form that is left over after subtracting the form of the model from the form of the association. When there is a leftover form in the residual plot, the form of this association and the form of the model are not the same. However, if the form of the association and the form of the model are the same, the residual plot should have no form other than random scatter. So essentially in this case, random scatter is good. You are looking for random scatter in your residual plot. So once we have all the residuals, we can measure how well the line makes predictions with the standard deviation of the residuals. So if we were looking at our Super Bowl data, we would not move forward with this because that line is better fit with, that form is better fit with a curve. But if we're looking at our Ford F-150 data, we can move forward and we can measure how well the line makes predictions. We use an abbreviation of S for the standard deviation of the residuals. The standard deviation of the residuals, S, measures the size of a typical residual. Remember, again, residual is how far the actual value is from the predicted value. So it measures the size of the residual. So smaller is better here. That is, S measures the typical distance between the actual Y values and the predicted Y values. So we've got some complicated calculations here to do all this, and you don't need to write down all of this in your notes. To calculate the standard deviation of the residuals, we square each of the residuals, add them, divide by n minus 2, and take the square root. So there's your formula there. You don't need to write that down. But let's look at our Ford F-150 data. We calculated a residual of negative $4,765 for the Ford F-150 with 70,583 miles and an actual price of $21,994. To interpret that, we would say that the price of the truck was $4,765 less than predicted, based on the number of miles it had been driven. And here was our regression equation. Here are all of the residuals. This was just one of the residuals. Here are all of the residuals for all of our pieces of data. And then there is how we calculate our standard deviation. So we have a standard deviation of $5,740. I want you to note that we won't ask you to calculate this value by hand. We wanted to show you the formula so that you can see some of the background. It's important that you recognize that we're using the residuals to find this. Google Sheets will do this for us. It's more important that you're able to interpret it. So let's talk about how to interpret it. In lesson 2.5, we used a least squares regression line to model the relationship between the price of a Ford F-150 and the number of miles it had been driven. We found that the standard deviations of the residuals for this model is $5,740, and that came from this slide. Remember, we're not going to ask you to calculate it by hand, but you need to understand that we're finding the sum of the squared residuals. So we subtract to find the residual, we square it, we add it up, we divide by n minus 2, we take the square root. We have to do this for every single piece of data, which is why, again, no one does this by hand. We use software to do that for us. So let's talk about how to interpret it. The actual price of the Ford F-150 is typically about $5,740 away from its predicted price using the least squares regression line with x equals miles driven. So here's something important to put in your notes for interpreting your standard deviation here, interpreting S. To interpret S, here is a script you can follow. The actual value is typically about blank, which is where you would put whatever your S value is, away from its predicted value using the least squares regression line with x equal to whatever x is. In this case, x equals miles driven. In this case, S is 5,740. I'm not filling in these blanks. This is a script that I want you to write down so that when somebody asks you to interpret the standard deviation, you can look at this script. I want you to make a note that you should replace the word value with whatever we're talking about. Like, I didn't use the word value here. What I said was the actual price of a Ford F-150. It's whatever's on your y-axis, so you might want to make your note. It's the price of a Ford F-150. Whatever the y-axis label is, that's what we're talking about. We give both the y-axis label and the x-axis label because the x-axis label goes right here for miles driven. So let's talk about a different measure of how well our model fits, the coefficient of determination, which we're going to call R squared. You will not often hear anybody use the phrase the coefficient of determination. The coefficient of determination is called R squared. Besides the standard deviation of the residuals, we can also use the coefficient of determination to measure how well the regression line makes predictions. Remember, that's what this whole lesson is about. How good is our regression line making predictions? So here's our definition. The coefficient of determination, R squares, measures the percent reduction in the sum of squared residuals when using the least squared regression line to make predictions, rather than the mean value of y. In other words, R squared measures the percent of the variability in the response variable that is accounted for by the least squares regression line. That's a lot. Let's take a minute and get that in our notes now. Suppose that we wanted to predict the price of a particular Ford F-150, but we didn't know how many miles it had been driven. Our best guess that you would have come up with before this class is you would have just found the mean. You would have found that Y bar, which is $27,834. This prediction is unlikely to be very good, as the prices vary quite a bit from the mean. If we knew how many miles the truck had been driven, we could use the least squares regression line to make a better prediction. How much better are predictions using the least squares regression line with x equals miles driven rather than using only the average price? So I really like this question for thinking about what R squares means. R squared tells us how much better the predictions are using the least squares regression line rather than using only the mean. The mean's not going to be very good because we already found our standard deviation was 9,570. In other words, R squared tells us how much better our predictions are, using the regression line than just looking at the mean. I would put this in your notes now. So here we've got something that we don't need to be able to make, but I wanted to show you. What we've got here is a scatter plot showing the squared residuals. So we've got those dots, we've got the distance from the residual or from our regression line, and we're squaring that. That only is when we are using the average price as our predicted value. For B, the scatter plot shows the squared residuals along with the sum of the squared residuals when using the least squared regression line. So this is just when we're using the mean. This is when we are looking at the residuals. I want you to notice the size of the boxes. Smaller is better. Smaller means we are closer to what we have predicted. To find R squares, we calculate the percent reduction in the sum of the squared residuals. So here we've added up the sum of all these squared residuals. Here we've added up the sum of all these squared residuals. We're going to subtract them and divide by what we got in A. And we get 0.66. Again, you will not be calculating this by hand. You will be using Google Sheets to calculate this. The sum of our squared residuals has been reduced by 66%. So here's a great interpretation. 66% of the variability in the price of a Ford F-150 is accounted for by the least squared regression line with x equals miles driven. So essentially, we can account for 66% of the variability by using the regression line instead of the mean. The remaining 34% could be due to other factors, including age, color, conditions, and other features of the truck. That was not included in this study. So, the easiest way to calculate R squared is just to square the value of the correlation R. You get that when you make your regression line on your Google Sheets. So you can just take whatever you get for R and you just square it. So you would just do R squared is equal to R times R. You just multiply R times itself. Again, we're not going to calculate this number by hand. It's more important that you know how to interpret it. So let's look at an interpretation. The interpretation of R squared. Again, I would put this in your notes. Make sure you label it clearly. How do we interpret? The sum of the squared residuals has been reduced by, right here goes whatever you got for your R squared, whatever your percentage is. You put that same percentage here. So in this case, 66% of the variability in the value is accounted for by the least squares R regression line with x equal to whatever is on your x-axis. Note that, again, we replace value here with whatever is on the y-axis. I've given you like a fill in the blank to interpret your R squared here. So what we've given you is two ways to tell, essentially, how good is the fit of your regression line. Both are calculated from the sum of the squared residuals. Both attempt to answer the question, how well does the line fit the data? The difference is only in the units. This piece right here actually really helps me to understand in my brain what it is that I'm finding here. The standard deviation of the residuals gives us the size of a typical prediction error in the same units as the response variable. In the truck example, S was equal to $5,740. Ideally, S is close to 0, indicating that our predictions are very close to the actual values. R squared is different. It does not have units. Again, it's still calculated from the sum of those squared residuals, but it's usually expressed as a percentage between 0% and 100%. Ideally, the value of R squared will be close to 100%, indicating that the model accounts for almost all of the variability in the response variable. Because these values assess how well the line fits the data in different ways with different units, most statistical software reports both. All right, after this lesson, you should be able to use a residual plot to determine whether a regression model is appropriate. See the additional video in Google Classroom on using Google Sheets to do that. You need to be able to interpret the standard deviation of the residuals, which is S, and you also need to be able to interpret R squared.